Hello friends. In last lecture we have discussed about the noise present in biomedical signal, or I can say bioelectrical signal recordings. Now in this lecture we will discuss about the filtering of biomedical signals. Here we will mainly talk about electrical filter. An electric filter is a circuit that can be designed to modify, reshape or reject unwanted frequencies. It can accept or pass only those signals that are wanted by the circuit designer. In other words, they filter out unwanted signals. Removal of noise from a signal is probably the most frequent application for signal processing of biomedical signals. It is also known as conditioning of the signal. The distinction between the noise and the desired signal is an heuristic judgment that must be determined by the user. Now suppose you are in a lecture room and you are listening to the lecture. If there is some tune playing outside or some music is played outside and you like that music, then the lecture could be the noise to you. But those who are interested in listening to the lecture, for them that music can be the source of noise. So that depends on the interest. The main purpose of filtering is the removal of the noise with the least possible distortion of the desired signal. Now let's discuss about two types of filters. On the basis of component, we can divide the filters into two types: active filters and passive filters. Now let's see how one is different from the other. Passive filters are based on the combinations of resistors, inductors and capacitors. Whereas if I talk about active filters, with R and C component, it also includes active device such as operational amplifiers, or we normally call it as op-amps. Passive filters attenuates the signal. So mostly the gain, that is output by input, can be less than unity. But if I talk about active filters, because active device is involved, then gain can be adjusted. Now passive filters are not limited by bandwidth limitations of op-amps because they don't involve any active device. But that's why it is suitable for high frequencies. Now if I talk about active filters, it is limited by the bandwidth of the op-amps, so they are mainly suitable for low frequencies. As in passive filters there is no active device involved, so no external power source is required. But in active filters we require an external power source. Also at low frequencies, if I talk about passive filters, because of inductors, if you use at low frequencies the size will be more. So passive filters at low frequencies are bulky, but in active filters small size could be possible. Passive filters are relatively cheap and active filters are comparatively expensive as compared to the passive filters. Now next we will further see the techniques used in filtering. They can be time domain and frequency domain filtering. Time domain filtering, we will start with time domain filtering. It has the biggest advantage that it is faster than all other techniques because it is directly working on time domain signal, not on frequency domain signal. And in this there is no spectral characterization of the signal or the noise is required. So that makes it easy to apply. But the only disadvantage it has is that there is no control on how it will work. That means it will work based on the assumptions depending upon the type of noise or signal. Now first example in the time domain filtering is the synchronized averaging. Linear filters fail when the signal and noise spectra overlap. So synchronized signal averaging can separate a repetitive signal from noise without distorting the signal. Let's see how it works. Consider a signal YKN. You can see it is just, we are taking it as an observed signal, or it is just one realization of the signal, or I can say one output that we have obtained from any analysis or any experiment. That could be EEG, that could be ECG signal, any signal it can be. Here k, small k, represents ensemble index, means how many realizations we are taking. That will run from 1 to m. Let's suppose if we are taking m number of realizations, we will keep capital M. Similarly, n represents the number of time sample index. So here capital M are the number of realizations, events or copies we are taking for one particular signal, and n are the number of samples in each signal. Now you can see YKN is obtained as the input, that is uncorrupted signal, XKN, and in that we have added noise that is represented as eta kn, which is the noise in the kth copy of the signal. Now here we are interested in removing that noise. Actually we want to get rid of that noise component. Now suppose for each instant of time, if we add m copies of signals, let's see like this, that means we have to include summation, we have to include this index k. K is now running from 1 to m, but n is what? N is the number of time samples in one signal, and if for one signal we have n number of samples, and how many realizations we are taking for that signal, that is capital M. So we have introduced here the index k, which is running from 1 to m. Now let's suppose if the repetitions of signal are identical and aligned, then it makes xkn as like summation k equal to 1 to m for xkn will be nothing but m xn. This is in particular if we have mentioned like it should be properly aligned, fine, then you can say that this is m into xn. It is very important to align the signal properly. Now if noise is random with zero mean and variance as sigma n square, then the summation, if we do particular like we have done summation for this, then if we increase the number of realizations, that means if capital M we are increasing, then this summation noise will approach to 0, but the variance will be like m times of sigma n square. The RMS value of noise in the average signal now becomes root m sigma n. From there we can calculate the SNR, that is signal to noise ratio, in the output that will be given by m divided by root m. It will be equal to root m times the signal to noise ratio in the original uncorrupted signal. So that means by synchronizing averaging, what we are doing is we are increasing the SNR. As we are increasing number of realizations, that means we will increase the SNR. Now let's see the brief description of the algorithm. So first is what? We have to obtain the multiple realizations of the signal of interest. Next is we have to find the reference point for each realization. Reference means that can be a trigger point, that can be like if I talk about ECG signal, QRS complexes, I can fix that alignment, or it can be the onset of stimulus, anything. You can see in this graph also, this 0 time instant can be the point of trigger, so we can align all the signals, all the trigger points at the same point, and then we can do the summations. Then same we have to align and add. After obtaining the reference point, we have to align and add the obtained copies of realizations. And last step is what? We have to divide the result by number of realizations added. Now you can see in this figure we have different number of copies of realizations taken, aligned, added and finally averaged to produce an almost noise removed signal. In that we have taken like one signal, then we have taken 4 realizations, we have aligned, added and finally averaged, then 9, then 16, then 25, continuously it is increasing. So as the number of realizations are increasing, you can say SNR or noise suppression is also increasing. Now the major advantage of synchronized averaging is that no frequency domain filtering is performed and no spectral content of the signal is lost. But the most important requirement in the synchronized averaging is that the realization of signals that are added must be aligned such that the repetitive part of the signal appears exactly at the same instant in each realization of the signal. If it is not done, what will happen? then the waveform of the event in the signal will be blurred or smudged along the time axis. And also, what is the other disadvantage of this? Because we want number of realizations. If number of realizations will be more, let's say I am taking 100 realizations, then how much SNR will be improved? Root 100 means 10. 10 times will be the SNR. So if I want to improve the SNR more, that means I have to increase the number of realizations. That means for long time patient has to sit, because it should be same patient, same system, same time. We have to take the realizations. So that will be a time consuming procedure, and also it will be tough for the patient. So when ensemble of several realizations of an event is not available, then synchronized averaging will not be possible, or it will not produce the good results. So for that, in next lecture we have another technique. We will discuss about moving average filters. So for now, in this lecture, it is that much only we have to discuss. Thank you so much.